Hi, I'm Cole.
And I'm Grace. Welcome to the Deep Dive.
Welcome to the Deep Dive, where we try to cut through the noise and get straight to the core of what you need to know.
Yeah, let's jump right in.
Okay, so think about artificial intelligence for a second. I mean, it's everywhere, isn't it?
Oh, absolutely. Your phone, scientific research, it's really changing things.
Totally. From predicting your next word to, speeding up science.
Mm-hmm.
But have you ever stopped to think about who actually, built the foundations for all this? Who were the architects?
That's such a critical question because honestly, a lot of what AI does now rests on work that was, well, pretty unconventional back in the day, niche even.
Right. And today we're diving deep into one of those key architects, Yoshua Bengio.
A central figure, definitely.
Yeah, he's part of our AI Visionaries, the Founders Playlist, where we're spotlighting the people who really, truly shaped this field.
So our mission today really is to unpack Yoshua Bengio's work. We're talking deep learning, neural networks, representation learning.
And his collaborations, right? Those were crucial.
Absolutely. And how his vision basically took AI from this sort of academic curiosity to a technology that's, well, fundamental now.
And to guide us, we've got some solid sources. We're looking at the official ACM-AM Turing Award recognition.
Which is huge, like the Nobel Prize of Computing.
Exactly. Plus, insights from Bengio's own papers, loads of them, and info from the Mila Institute he leads. So, a pretty comprehensive view.
Okay, so to really get Bengio's impact, you have to picture the scene, maybe early 2000s. Neural networks, they've been around since the 80s, but honestly,
But people weren't buying it.
not really. The wider AI community was pretty skeptical. It was tough going. But Bengio and Geoffrey Hinton and Yann, LeCun, they stuck with it. Real perseverance.
And that persistence, it really paid off, didn't it? Big time. 2018, they jointly get the Turing Award. Why was that specific award such a massive deal?
Well, it wasn't just an award. It recognized their conceptual and engineering breakthroughs. That's key.
Okay, so not just theory.
Right. They weren't just, fiddling around. They developed core ideas, ran experiments that showed really surprising things, and crucially, made engineering advances that proved deep neural nets actually worked in practice.
They showed they were practical.
Exactly.
Yeah.
Not just a curiosity, but a critical piece of modern computing.
And the impact was just, wow. The deep learning methods that came out of their work, they led to these incredible breakthroughs: computer vision, speech recognition.
Natural language processing, robotics.
Yeah, think about your smartphone, the stuff it does now. Just 10 years ago, impossible, right? Totally impossible. And what's really interesting is how deep learning works. It's not like old school programming where you tell the computer every single step.
Right, no explicit instructions.
Instead, the computer uses an algorithm to learn to sort of extract patterns from data. Like it figures out what pixels mean cat, not because we told it about pointy ears and whiskers.
But just by looking at tons of cat pictures. Exactly. It adjusts its internal connections, its weights, again and again, until it just gets what a cat looks like in the data. It tunes itself.
And this huge leap forward wasn't just them, right? There were other factors.
Oh, definitely. Two big things really helped amplify their work. First, powerful GPUs, graphics processing units.
The things gamers love.
The very same. Turns out they're amazing at the kind of parallel math deep learning needs. And second, just access to massive amounts of data.
So powerful computers plus tons of data.
It was the perfect storm, yeah. Led to what the Turing Committee called leapfrog advances. Things moved incredibly fast.
And the connection between Bengio, Hinton, and LeCun, it wasn't just that they were working on similar things.
There was real synergy.
Yeah.
Yann LeCun actually did his postdoc work under Hinton.
Oh, interesting.
And then LeCun and Bengio worked together at Bell Labs back in the early 90s. Even when they weren't collaborating directly, you can see how their ideas bounced off each other.
Like a feedback loop.
Yeah, exactly. And they're still working together in a sense through this GIFAR program, looking at how machine learning connects with neuroscience, with how our brains work. Really fascinating stuff.
Okay, let's dig into some of Bengio's specific contributions. You mentioned representation learning earlier. What exactly is that?
Right, so representation learning was a big focus for him. It's basically about getting the AI to learn the important underlying features from the data itself.
Instead of humans telling it what features to look for.
Precisely. Humans didn't have to hand engineer things like look for edges or look for texture. The AI learns the best way to represent the data to solve the task.
Why was that so important?
Because training really deep networks, ones with lots and lots of layers, was incredibly hard. There was this kind of chicken and egg problem.
Chicken and egg. How so?
Well, think about recognizing an object. The lower layers of the network need to find basic features like lines or corners. But which features are important? That depends on what the higher layers are trying to do, like identify the whole object.
Ah, so the bottom needs the top and the top needs the bottom.
Exactly. He was a real tangle.
Yeah.
Models often just got stuck, couldn't learn effectively.
Sounds like a potential dead end. So how did Bengio and his collaborators manage to, crack that? What was the breakthrough?
A huge breakthrough came from a paper Bengio co-authored, asking, why does unsupervised pre-training help deep learning?
Hmm.
The core idea was, well, think of it like a warm-up.
A warm-up for the AI?
Sort of, yeah. Before tackling the main task, like classifying images, they first trained the network in an unsupervised way. Just let it look at the data without specific labels to get a feel for the underlying structure.
Okay.
This pre-training essentially tuned the network's initial settings. It put the model in a good starting place, guiding it towards finding useful patterns rather than getting lost.
So it's like giving it a map before the main journey.
That's a great analogy. It acted like a regularizer, pushing the learning towards solutions that actually generalize well, meaning they worked on new data, not just the stuff they were trained on.
And this made learning more robust, less sensitive to just random starting points.
Exactly. And crucially, it allowed them to train deeper networks successfully. They mentioned getting 4-layer models working, where even 5-layer ones had failed before without this pre-training. It helped break that chicken and egg cycle.
Wow. And did this advantage fade as they got more data?
Interestingly, no. The paper found the benefit didn't really diminish with bigger data sets. It acted almost like a technique to reduce randomness or variance in the learning process, making it more stable overall.
Okay, so that's representation learning. What about his work on sequential data? Language, prediction. That sounds vital too.
Hugely vital. Back in the 90s, Bengio was already working on combining neural networks with other methods, like hidden Markov models, to create probabilistic models of sequences.
And this wasn't just theory.
No, not at all. These ideas were actually baked into a system AT&T used for reading handwritten checks. Think about that for the 90s. That was a massive practical win for neural nets.
That's incredible for that time.
And modern speech recognition. A lot of the core concepts build on that early work.
Then came that 2000 paper, the Neural Probabilistic Language Model. What was so special about that one?
That paper was huge. It introduced the idea of using high-dimension word embeddings, basically representing each word as a point in a complex mathematical space.
Like giving each word coordinates.
Kind of, yeah. And words with similar meanings end up closer together in this space. It was a revolutionary way to capture word meaning for computers.
And the impact.
Massive. It had a huge and lasting impact on pretty much all of natural language processing, translation, question answering, even understanding images based on questions.
And his group didn't stop there, right? You mentioned attention mechanisms.
That's right. They introduced a form of attention mechanism. This is another game changer, especially for machine translation. It allows the model to focus on the most relevant parts of the input sequence when generating the output.
Like how we focus on certain words when listening.
Exactly. And that concept, it's now a fundamental part of the big models we hear about all the time, like transformers. Absolutely key.
Okay, from understanding language to creating things. Let's talk about generative adversarial networks, GANs.
Ah, GANs, yes. Developed by Bengio and Ian Goodfellow starting around 2010. These things just sparked a revolution, especially in computer vision and graphics.
How do they work? I heard it's like two AIs battling each other.
That's a pretty good way to put it. There's this dichotomy. You have one network, the generator, trying to create realistic data, say, images of faces.
Okay.
Then you have another network, the discriminator, whose job is to tell the difference between the real images and the fake ones made by the generator.
So one's forging, the other's detecting.
Exactly. And they learn together through this constant feedback loop. The generator gets better at fooling the discriminator, and the discriminator gets better at spotting the fakes. It's this adversarial process that pushes the generator to create incredibly realistic output.
And the result is AI that can actually create original images.
Yes. Stuff that looks genuinely novel, creative even. It was a huge step from AI just recognizing things to AI generating things. Really reminiscent of human creativity in a way.
Which brings us to a more recent shift in Bengio's work. As AI got more powerful, he started focusing more on safety, right? Around 2023.
That's right. A significant pivot. He started looking at AI safety, basically. What could go wrong as AI gets smarter, potentially reaching or exceeding human intelligence? And critically, how do we design it so it doesn't harm us?
What prompted that? Was it something specific he saw?
Well, he pointed to these growing tendencies in some advanced AI models towards things like deception, manipulation, even self-preservation.
Really? Like the AI trying to protect itself?
It seems so in some experimental setups. And he saw these as warning signs, potential catastrophic risks, if we end up with super capable AI that isn't perfectly aligned with our goals, with human well-being.
So what's his vision for safer AI? He talks about this scientist AI, doesn't he?
Yes, that's his long-term research goal. The idea is to build AI that's fundamentally different from current models that might just imitate human behavior, good or bad, or try to please us.
How is the scientist AI different?
It's designed to be like an idealized scientist. Its goal is purely to understand, explain, and predict the world accurately and honestly. Not to persuade, not to achieve external goals, just understand.
Like a psychologist studying a sociopath but not becoming one.
That's the analogy
Well,
he uses, yeah. It understands harmful behavior without adopting it. Practically, he sees it acting as a kind of safety guardrail.
a guardrail. How?
It could evaluate actions proposed by other, perhaps less trustworthy AI agents. It could answer questions like, how likely is this action to cause harm? And if the probability is high, the action gets blocked.
Interesting. A built-in safety check.
Exactly. And beyond safety, he thinks this kind of AI could also massively accelerate science by generating plausible hypotheses in complex areas like medicine or climate change.
That connects to another big area for him, causal representation learning, moving beyond just finding patterns.
Precisely. He co-authored this paper towards causal representation learning, pushing for machine learning to incorporate principles of cause and effect.
Why is that important? Don't current models find useful patterns?
They do, but they mostly find correlations. They learned what things tend to happen together in the data they've seen. Causal models aim higher.
Higher how?
They try to understand the underlying mechanisms. They predict what happens if you intervene, if you change something. This gives you much more robust knowledge that holds up even when conditions change.
Like the classic example, storks and babies.
Exactly. Statistics might show a correlation between stork populations and birth rates in some areas, but a causal understanding tells you sending more storks won't actually increase births.
Right, correlation isn't causation. Accurate predictions aren't enough if you don't know why.
You got it. And a key concept here is the independent causal mechanisms principle. The idea is that the world, or the process generating the data, is made up of independent modules or mechanisms.
Like different parts of a machine.
Sort of. And if you can model these independent parts, your AI becomes more robust, easier to understand, and better at transferring knowledge to new situations. It helps disentangle the underlying factors.
How does this help with problems in machine learning today?
Well, one big area is learning those disentangled representations we talked about earlier, like truly separating the concept of an object from its position or the lighting in an image. Causality helps define what these independent factors are.
Okay, makes sense. Any other applications?
Yeah, think about reinforcement learning, where AI learns through trial and error. Causal reasoning can make RL agents much more efficient. They can reason about the consequences of their actions, do what if, or counterfactual thinking. What would have happened if I'd done that instead? That boosts learning speed and performance.
And in science, you mentioned that earlier.
Right. Causal models are super valuable there. For example, understanding complex medical phenomena, like why COVID fatality rates look different in different groups. Causality helps untangle confounding factors.
And astronomy, too.
Yes. They use causal principles to filter out instrument noise from the Kepler Space Telescope data, basically separating the telescope's glitches from the effect, the actual light from stars. This helped confirm exoplanets, including one called K2-18b, where they later found signs of water. Removing the noise revealed the true signal.
Wow. So his impact isn't just research papers, is it? He's built things, too. Mila.
Oh, hugely important. He founded and is the scientific director of Mila, the Quebec AI Institute.
And it's big.
It's the largest academic deep learning research center in the world. Over 1,200 researchers. It's massive.
What's Mila's focus? Just pure research?
Research is core, but the mission is broader. AI for the benefit of all, with a really strong emphasis on responsible and beneficial development.
So ethics are built in.
Very much so. They have initiatives like an AI for Climate studio, using AI to fight climate change, and an AI policy fellowship, It's about impact.
And Bengio himself, he's received a lot of recognition beyond the Turing Award, hasn't he?
Oh, yeah. Officer of the Order of Canada, Fellow of the Royal Society of Canada, Time Magazine's 100 Most Influential People in 2024. He's also on the UN Scientific Advisory Board. His influence is global.
And he's active on the ethics front personally, too.
Definitely. He was heavily involved in the Montreal Declaration for the Responsible Development of AI, and now he's chairing the big International AI Safety Report. He's really at the forefront of trying to guide this technology responsibly.
Which feels necessary given the public conversation around AI right now. It's pretty intense.
It really is. You see all sorts of perspectives. Deep concerns about safety and control, people worried about superintelligence running amok.
But also skepticism, right? People saying current AI is overhyped.
Absolutely. You hear folks calling large language models glorified search engines or just fancy text predictors, arguing that true AGI is nowhere near and maybe not even the real danger.
And then there are the environmental worries.
Huge ones. The energy and water needed for these massive data centers. Concerns that AI could actually make the climate crisis worse.
Plus the economic impacts jobs, especially entry-level ones, the potential for an AI bubble to burst.
It's a really complex mix of hope, hype, and genuine concern. And Bengio's focus now on safety, on this scientist AI, on causality. It feels like a direct response, an attempt to navigate these incredibly tricky waters.
So wrapping this up, Yoshua Bengio's story is quite something. From that early, almost stubborn belief in neural networks when few others shared it.
Right, through foundational work in deep learning, representation learning, GNs.
He's just profoundly shaped the AI we have today. And now he's trying to shape its future, pushing hard for safety and responsibility. It's quite a legacy already.
It really is. Which leads to maybe a final thought for everyone listening.
Go for it.
Well, if Bengio's right, if truly robust, reliable AI needs to understand causality, needs to reason about interventions and what-ifs, moving beyond just finding correlations. What does that mean for us? How should we as humans approach understanding our own complex world? Do we rely too much on correlation and not enough on digging for the real causes when we make decisions?
That's definitely something to chew on. Relying on patterns versus understanding the why. A deep thought indeed.
Thanks for listening. If you enjoyed this episode, please like, subscribe, and share. It really helps us grow. See you next time.